Hello and welcome. You are looking at classifying quadrilaterals. Alright, in order to classify the specific and special kinds of quadrilaterals, let's first kind of get an idea of what a quadrilateral is. So it's a four-sided shape, also has four angles, hence the quad part. Two diagonals can be drawn through any quadrilateral. So for example, if I draw a line there, that's a diagonal. It goes from opposite angles in this case. And there are two right there. There's also an intersecting point. We can talk a little bit about that and the length of the diagonals in certain special quadrilaterals. I just mentioned opposite angles. They're angles that kind of face opposite each other. They do not list themselves consecutively. No matter how the quadrilateral is drawn, you will always have opposite angles. And opposite sides. So again, no adjacent sides. So this side and this side are opposite, much like this side and this side. It won't matter too much in this general quadrilateral, but in very specific ones it will matter. There's a 360-degree interior angle sum, which means that if I add up this angle with this angle and this angle and this angle, I will always get 360 degrees, no matter the size or shape of the quadrilateral, as long as it is a quadrilateral. So even though none of these are known to be congruent or said to be congruent, even though that looks like 90 degrees, who knows? This plus this plus this plus this equals 360, regardless. And you can think of that from like a square, if you really know what a square looks like. 4 90-degree angles gives you 360. It's consistent with any quadrilateral. And the exterior angle sum, which is true of any polygons, also equals 360 degrees when you add them up. So that angle, can't really see it after I extend it, but that angle there, and 3, and 4. I will not make any mention of exterior angles during this actual lecture, but it's good to know. Now, I have here asterisked in blue. Special quadrilaterals will be referenced, and they will possess specific properties. So I'm going to be listing 6 different, kind of 7, but 6 different quadrilateral types during the next few sets of slides with examples on how to solve for certain variables using whatever. The more specific quadrilateral types will possess all the properties its less specific quadrilateral types have, and then some. This will make more sense when I do my final slide, which has more to do with the fact that as you get, like, for example, I'll give you the example, the square, to me, is the most specific type of quadrilateral that you can get, and there are specific reasons behind that. Now, a less specific example of a square is a rectangle, and a square occupies all properties that a rectangle has, and then it has a few more. So I'm going to go ahead and go on to the next slide. And you're looking at the parallelogram. Now you can see in here will be the definition of the parallelogram and the drawing that helps define it. Then I'm going to list some other properties. These kinds of properties, something that's more specific than a parallelogram, will also occupy these properties. So that's all that means. Anyway, let's go. A parallelogram is a quadrilateral where 2 pairs of opposite sides are parallel. So these 2 opposite sides are parallel, these 2 opposite sides are parallel. Now that's at the very least the definition, so as long as you know that information, then you know you have a parallelogram. Here are other things that can tell you that you have a parallelogram. Here are other properties that happen, which will be proved in another video later, that will explain how I can prove this, etc. This one we should already know. Opposite sides of a parallelogram are congruent. So not only are the opposite sides parallel, they are also congruent, like so. Okay, that's one, and that's good to know. Opposite angles of a parallelogram are congruent, so we just mentioned opposite angles. Here's a set, here's a set. Everywhere a set, boom. The diagonals of a parallelogram bisect each other. So, although I'm kind of short on room, let's kind of just draw through this so you can see there's a diagonal, there's a diagonal. Now, as I drew these two, no, the diagonals are not necessarily congruent. It would be a shame to make that assumption. However, this represents the midpoint of both diagonals. So this segment is congruent to this segment, and this segment is congruent to this segment. I know I'm kind of botching up this drawing, but you can really see that here. The last one here is consecutive angles of a parallelogram are supplementary. Now this should already be known in the sense that you have probably covered a unit that states that if you have parallel lines and a transversal that's drawn through them, then same side interior angles, if this is x and this is y, are supplementary. In other words, x plus y equals 180. Same is true of the other transversal, only this would be y and x because these are congruent. Now, it can still be proved, but I'm going to go by the same side interior angles mumbo jumbo for now. Also, these two lines are parallel, so when a transverse cuts through them, here's y and x, which also equals 180, and x and y once again. So I might not spend too long on all the properties every single time. I'd rather do more of the examples while I list these and draw them, but at least now you have an idea. So the first example here, let's find the value of x in parallelogram PQRS, then find, this is not drawn here, let me PQRS, there we go, and then let's call this E, F, G, H according to this one. Something I guess I neglected. Okay, then find the value of Q, R, and P, S thereafter. Okay, to find x, what you have to do is recognize that they tell you it's a parallelogram. Okay, and because of that, you do know a property of a parallelogram that opposite sides are congruent. So these two lengths are equal. So I can make an equation where they're equal to each other. 3x minus 15 equals 2x plus 3. Subtract 2x and add 15, you'll get x equals 18. So QR is 3 times 18, which is 54, minus 15, which is 39. PS should be the exact same thing. I shouldn't have to do any more work, but if you do want to double check, 18 times 2 is 36. 36 plus 3 is 39. Both 39 units each. There you go. Make sure you always answer the question. Don't just solve for x. Make sure you give them what they want. Okay, find the value of y in parallelogram EFGH, then find the measures of these four angles here. Now before I begin, I'm just going to clarify with that same exact thing that E and G should be the same angle measure because it's a parallelogram, and F and H, also opposite angles, should be the same angle measure. E and F should not be. However, they should add to 180 degrees. So 6y plus 4 plus 3y plus 32 should equal 180. These are supplementary. 6y plus 3y is 9y. 4 plus 32 is 36. And you get 144 here, so y should equal, what is that, 16, I think? So if y equals 16, I don't have much room here. Measure of angle E. By the way, yeah, for a lot of these examples, I pre-apologize if I end up erasing work because I gave myself very little room to work with. Measure of angle E is 6 times 16. Let me do that in my head. 96 plus 4 is 100. Now again, save myself some work. I'm going to trust I got that answer right. I'm not certain, but I'm going to trust I did, in which case measure of angle F will have to be 80. I already know that these should add up to 180. Measure of angle G should be the same as E, which should be 100, and H should also be 80. There's no double checking measure for these two because there's no expressions here. However, you could double check with F. You'll be good. That's a parallelogram. Those are two examples. Not using diagonals. I'll use diagonals in some future problems. Okay, the rectangle. The definition of a rectangle is all of your angles are right angles. They're all 90 degrees. And that's it. You're good from there. So the first property then that you can get out of that, opposite sides of a rectangle are parallel. Now that's true using actually a theorem that was used a while back that referenced if you have a line that's perpendicular to two lines, then those two lines are parallel. Also, these are interior, same side interior angles, and they are supplementary because they both add to 180. So boom. The diagonals of a rectangle are congruent. Now, unlike the last example where I just said they bisect each other, which in this case it looks like they do too in property number 4, these also are the same angle side length. Measure, whatever you want to call it. Same segment length. Which can also be proved. Okay, opposite sides of a rectangle are congruent. That kind of makes sense. Kind of look at that. And the diagonals of a rectangle bisect each other. Now, not only do they bisect each other, but because the diagonals are congruent, then these segments that are bisected are all the same segment together. Like this and this and this and this are all the same. They all meet at this midpoint. Okay, so let's do the first example here. With these diagonals, I remember when I set this up that I wanted to make 2y plus 4 represent the entire diagonal, not just this little part, and 6y minus 5 represent the entire diagonal. Same idea. So find the length of the diagonals in the rectangle below. So they do not ask you to solve for y. That doesn't mean you don't need to solve for y to solve the problem, but make sure you don't just finish by solving for y. Because the diagonals are congruent, I can set these lengths equal to each other. Okay. It's 4y equals 9, and y equals 2.25. Strange number. We got to deal with it. It happens. So the length of both diagonals should be the same. I should be able to sub 2.25 into either one. I'll do it in 2. I like multiplying that by 2 a little more easily. So the length of the diagonal, I'll just put diag, equals 2 times 2.25, which is 4.5. 4.5 plus 4 is 8.5. And I trust I get the same answer using 6y minus 5. So the length is that. Okay, find the value of y in the below rectangle. So here I'm referring to this angle measure. This is 3y plus 32 degrees. And this angle measure here is 6y plus 4 degrees. So a couple things you probably want to work with here, depending on how savvy you are with it. Good to know, first of all, that these are right angles. So here's a right angle here, here's a right angle here. You can do a lot of things to work into what angle measure you want to work with specifically, but I have to make an equation that involves both of these. Now I know that these are right angles, so I do know that their complements are the other portion of that angle. So for instance, this guy's complement is right here, and this guy's complement is right there. So you can use either one and it might help you. I'm going to go ahead and use this one right here because it's part of the same triangle. This angle measures 3y plus 32, like this guy right here. Well, this guy should also be the same, like not the same thing, but this is the same angle measure as this one. But I can use an expression using 6y plus 4 to figure out what that is. Now, I could do that. So I could say 3y plus 32 equals, now check this out, 6y plus 4 is this angle right here. This angle right here is 90 minus 6y plus 4 because this is the complement of it. There are a lot of ways that I could set up this problem and perceive it. This is the one I chose for you. So I'm subtracting 6y plus 4 from 90 to get the result of this angle. Okay, so 3y plus 32 equals, looks like negative 6y plus 86. So I add 6y, I'll get 9y equals 54. So y equals 6. And that's all they asked us to solve for. And you can double check and make sure that basically these two are supposed to add up to 90, this one and this one. It might help to say that, you know, these guys are congruent, these guys are congruent, stuff like that. You can work that way as well. Not a property that we listed because it's kind of strange to talk about. But one thing you can say, if you noticed here, I should have probably mentioned it, that because these diagonals bisect each other and because these segments are congruent, notice how I've made isosceles triangles. Here's an isosceles triangle, and all the rest are as well. And in an isosceles triangle, not only are two sides congruent, their angles opposite them are also congruent. So as you can tell, that's how I also know that those angles are congruent to each other. It's good stuff, right? All right, let's move on. Okay, now the rhombus. And I've been I'm arguing with myself over this, what the plural is. I always thought it was rhombi. But whenever I'm looking at textbooks and stuff, they are saying rhombuses. So I'm not sure if that's right. Doesn't matter. Okay. All sides are congruent in a rhombus, so it's a four-sided shape, quadrilateral. And I'm not saying it's the one that people forget, but don't mistake it just for a parallelogram. By the way, it does look like a parallelogram, doesn't it? There's something we're going to learn. Opposite sides of a rhombus are parallel. So a rhombus, here's one of those examples that I'm referring to. A rhombus is a specific type of parallelogram. I also should have mentioned, as I go back for one moment for you, a rectangle is also a specific type of parallelogram. Notice opposite sides are parallel. What's different about it with the definition? It's like a parallelogram, but all the angles are right angles. Pretty interesting. A rhombus is like a parallelogram, but all the sides must be congruent. So again, a specific type. Each diagonal of a rhombus bisects the angles at its endpoints. So when I go from here to here and here to here, I have made sets of congruent angles. These two are congruent to each other. These two are congruent to each other, and they're all congruent to each other. Because you can see here in number 4, I know I'm skipping around, but opposite angles of a rhombus are congruent. So this angle is congruent to this angle, the full thing, and this angle is congruent to this angle, the full thing. So as I bisect this angle, I've also made 2 more sets of congruent angles. Kind of a lot to take in, but after you play with it, or if you take a look at what it looks like, you kind of believe it. Here's some more. The diagonals of a rhombus are perpendicular bisectors of each other. So not only do these guys bisect each other, and no, they are not congruent to each other, all 4 of them, just these sets. But not only is this true here, but these also intersect at 90 degrees. Here's a right angle. You can tilt your head, assuming I drew this right. It looks the same. This is a right angle, this is a right angle, and this is a right angle right here. So all 4 of them are also right angles. Okay, and I mentioned number 4. Number 5, consecutive angles of a rhombus are supplementary. This is very much like the parallelogram, also the rectangle. Remember, if a rectangle is a specific type of parallelogram, this must be true. I didn't add it here because I think you kind of have to see that 90 plus 90 is 180 there. Here you don't necessarily know what the angle measures are, but this plus this is 180. Once again, same side interior angles. We already are very aware of that. Let's go on to the examples. Solve for the variables in the rhombus below. So you have no sets of anything that you know for sure is what it is, but you do know that all 4 sides are congruent. So I can set any 2 equal to each other. The only one that's going to help me in the beginning is this set right here, because they both have the same variable. So 2x minus 5 equals x plus 8. Plus, they're not asking you to solve for the side of any rhombus. They're just asking you to solve for the variables. However, it looks like we will have to know. So x is going to equal 13. Now, I do have to plug this in. 13 plus 8 is 21. So each side length looks to be 21. So the next set of things that you can do is just say, well, these will equal 21. Those will be your next 2 sets of variables, or two equations. So z, for instance, I already know will equal 7. For the sake of time, I'm going to speed that up. And this one, 26 minus 5y equals 21. I'm going to go ahead and subtract 21 and add 5y to the other side. I'll get 5y equals 5, therefore y equals 1. And that will give you a length of 21 in all of your sides. Okay, find the measures of the numbered angles in each rhombus. Okay, so this is kind of interesting here. We have some work to do. You're trying to think, where do we start? Well, I can start with 1. I know this is a right angle, 90 degrees. Straight up, I'm already good to go. 50 degrees here is just for this angle measure here. Now this one is also the same angle measure. These are congruent because this bisected this diagonal, or the diagonal bisected this angle, diagonal also bisected this angle, and these 2 are also the same angle measure as 50. So measure of angle 1 is 90. Measure of angle 2 and measure of angle 3 are both 50 degrees. Okay. Now, measure of angle 4, you can do a couple of ways. I'll go and do one way that's kind of different. I'll talk about another way, actually. If this whole thing's 100 degrees, because you add 50 and 50, this whole thing is 80, half of that will be 40. So this is one way of doing it. A second way is looking just at this inside triangle right here. This is 90 degrees, this is 50 degrees. 90 plus 50 is 140, 140 plus 40 is 180. That gives you 40 as well. There you go. The square. This is the most specific type of quadrilateral, and I only say that in the way that you'll see what I mean. In terms of parallelograms, it's the most specific type. There are 2 other types of quadrilaterals that are not going to be in the same section as parallelograms and such. So the square, all sides are congruent and all angles are right. So a square is like a hybrid of a rhombus and a rectangle. The rectangle has all right angles, the rhombus has all sides congruent. The square has the combination of both. So any properties that both of these things occupy, even though they don't occupy the same exact ones, for instance, these ones don't have congruent diagonals. Well, these ones do have congruent diagonals, so the square will have congruent diagonals. These ones don't have right angles here. Well, these ones do have right angles here, so the square does as well, etc. Things like that. So everything that is a rhombus and a square will mesh together. So opposite sides of a square are parallel. Must also throw that in there. The diagonals of a square are congruent, much like I mentioned before. The diagonals of the square are perpendicular bisectors of each other, just like I was talking about. So perpendicular bisectors, and if you can imagine, all four of these are congruent to each other. And I should have said something else. Each diagonal of a square bisects the angles at its endpoints, and as you can imagine, they're congruent. Not only are they congruent, but you know what the angle measure is. Because the right angles are 90 degrees, and these are bisected, you know these are all 45 degrees each. Okay. So lots to take in with a square. It's like the perfect form of what you want. So example number 1, find the length of the side of the square, or of any side of the square, I guess, of a side. Okay, now I'm asking for the length of a side. What you're given are diagonal measures. Okay, a lot to take in with this problem because you have to go based off a lot of properties here. For starters, these two equal each other, these parts of these diagonals, so let's solve for x to begin with. Okay, 5x equals 15, so x equals 3. Okay, x equals 3, so each segment of this diagonal here is 13 units long. 13, this must be 13 as well. So we want to find the length of a side. What I can do next is, I've been referring to isosceles triangles. That's not going to matter too much here. What's going to matter now is that this is a right triangle right here. So if I draw that a different way, it looks more like this. Maybe it helps you out. This is 13, this is 13. I don't know, I'll call this C. I don't know what C is right now, and C is the length of a side of the square. That's what I'm looking for. So, Pythagorean theorem. 13 squared plus 13 squared equals C squared. For the sake of time, I'm going to save time and tell you that C is 13 times the square root of 2. You can approximate that to whatever that is, but that's how I'm going to give you the length. You'll figure out how special right triangles work in some ways eventually and later. Find the perimeter of a square whose area is 90 square meters. So a square has all congruent sides. That's one of the things to take in here, and this is base length and this is height length. So I know that whatever the base and height are, I know they're both the same, and I do know that when I multiply them, I should be getting 90. So x is the square root of 90, which is 3 root 10. So each length, each side is 3 root 10 units long. So what is 4 times that? What is adding all of them up together? That's 12 root 10. That's your perimeter. Right there. Again, trying to save time wherever I possibly can. Okay, I have two more shapes to go through, the trapezoid and the kite. So first the trapezoid. Now trapezoid and kite are way different from each other, but the trapezoid is also way different from all of the other 4 shapes I mentioned, and so is the kite. All depending on who you talk to. Now in this particular lesson, I'm going to play under the assumption that trapezoids must only have one pair of opposite sides be parallel. If you look around the internet or you find a certain book, they may not agree. I'm not saying whether I agree or disagree, but I want to make the trapezoid unique for the sake of explaining its differences compared to the other things. So I can't say a trapezoid can be made to be like a square or rectangle or rhombus or parallelogram, because a trapezoid can only have one pair of opposite sides parallel. The second pair cannot be parallel. Okay? So very, very specifically, a trapezoid cannot be a parallelogram. That's the definition of a trapezoid. Both of these things are called bases, the two that are parallel. This is a base and this is a base, even if this thing's on the top. An isosceles trapezoid's non-parallel sides are congruent, just so you know. So in an isosceles trapezoid, it looks like this. These sides are congruent and these are parallel. Okay. The diagonals of an isosceles trapezoid are congruent. So if the trapezoid is isosceles, I do know that this length here is congruent to this length right here. They do not bisect each other. They can't. In my case, that these are not parallel, but these lengths are congruent. The base angles of an isosceles trapezoid are congruent. So here is a pair of base angles right here and right here. These two are congruent to each other. These two up top are a pair of base angles. These are congruent to each other. They're not necessarily congruent to the other guys down here. And then finally, I didn't really know how to word this, but try and do the best you can with this. Consecutive non-base angles of a trapezoid are supplementary. Now, I didn't mention isosceles trapezoid. It doesn't have to be isosceles. But what I'm referring to is if this is x and y and let's use different letters, w and z. Let's assume w is not congruent to x, y is not congruent to z. X plus y is still 180 because these lines are parallel, and here's your transversal. W plus z is still 180 because these are parallel lines and this transversal is cutting through right here. Same side interior angles, same idea. So it doesn't matter whether or not doesn't matter whether or not it is isosceles. Even if it's not, they're still supplementary. So first set, find the value of x and y in the trapezoid below. Okay, one thing you should not do is you should not assume that these are isosceles right here, which means if these aren't isosceles, then there's no way to say that these two angles are congruent here. So I will not play off that assumption. You can play off the assumption, however, that these two are supplementary and these two are supplementary. So divide this kind of in half, if you will. This side has nothing to do with this side, except you can confirm that all four angles add up to 360. That's something you could do. Anyway, 5x plus 60 is 180, supplementary. So 5x is 120. So x equals 24. Okay. Y, if I add these up, 6y minus 5 plus 125 equals 180. 6y plus 120 equals 180. 6y equals 60. Therefore, y equals 10. And there you go. We solved them. Now again, we didn't know it was isosceles. I think a lot of people might make the mistake that you can set these equal to each other only if it is isosceles. Be very careful. Okay, find the length of TU and SV. If TU is parallel to SV, whoops, and TV is congruent to UV. Now before I actually begin this one, let me go back to this one. The fact that they called this a trapezoid, or that I did, means that you can mark these parallel. Now the fact that these are marked parallel says you can do the same side interior angle business. In this case here, I'm marking these parallel because they say that. I also want to say that these are congruent to each other. TV, this should not say UV, I'm sorry, this should say US. TV is congruent to US. Now, if a figure is an isosceles trapezoid, then the diagonals are congruent. The converse is also true. If the diagonals are congruent, then your figure is an isosceles trapezoid. Now, not only do I know that these two are parallel, I'm sorry, if these are congruent and if these are parallel, then you have a trapezoid. So, these two are congruent. Now I know it's isosceles, which means I know that 2x minus 1 and x plus 2 are the same measure. So x equals 3. Now I have to find out the length of TU and SV. Let's substitute. 3 for TU, or 3 for this. I get 6, and SV here, I get 12. Sorry for kind of the typo right here. It happens. Okay, the last one's the kite. Two pairs of adjacent sides are congruent. No sides are parallel. I'm just going to go ahead and jump right through so I can get to work. These two are congruent to each other. These two are congruent to each other. To keep that theme in play, I'm not going to allow this side to be parallel to this side or this side to be parallel to this side. I'm going to avoid the fact that it can be considered a rhombus. We're going to say it cannot be, meaning it can't fall into the parallelogram state or anything like that. Okay, so a kite specifically has that kind of figure. Sometimes they're drawn differently, whatever. Okay, opposite sides cannot be congruent in that same idea. If they can't be parallel, then they also can't be congruent for this particular case. The diagonals of a kite are perpendicular. Now these will not look diagonal. They'll look vertical and horizontal. However, they're not. However, they're called diagonals. These are perpendicular. Okay, this explanation here, just all I'm saying here is that these two parts are congruent. This diagonal bisected this diagonal, and it always will in a kite. It's not true the other way around. This one will not bisect this one, but this one will bisect this one. The one that represents the reflectional line of symmetry will bisect the other one. Kind of sweet. Okay, some examples here. Find the measure of angle 1, 90. I'm just going to save you some time right there. Measure of angle 2 and measure of angle 3 in the kite. Okay, so measure of angle 1 is 90. This also should be 90. This also should be 90, by the way. So now we know all of those. One thing that's not really mentioned, but you might be able to recognize the fact that both of these triangles right here, this one, let's see, this one in red and this one in green, well, this one in purple, are actually congruent using the HL property. Hypotenuses are congruent, right triangles, these legs are congruent. Also, these are obviously by the reflexive property or Pythagorean theorem. But HL property says those are congruent. So that means this angle and this angle are congruent using CP/CTC. So if this is 46, this is also 46. Other things I guess you could mention that these two, that the diagonal bisects these two angles here. I probably will list that as a property someday. Some other day. Okay, 3, if this is 46, this is 44, because 46 plus 44 is 90, and the two non-right angles of a right triangle are complementary. And that's it. Okay, example number 2, find the perimeter of the kite if AC is 21 and BD is 16. Okay, AC is 21 right here, BD is 16 right here. You also have BA as 10. Okay, 21 is not going to be divided in half. We can't just say, well, I know exactly where it's cut. However, 16 is cut in half. So let's go back here. This should be 8, and this should be 8. Okay. Now, given that this is 10, I also know that this is a right triangle, or a right angle right here, so I know this whole thing's a right triangle. I don't yet know what this is. I'll just call this x. So I can use Pythagorean theorem, x squared plus 8 squared equals 10 squared. To save time, I'm going to say that x equals 6. So x equals 6, that's not what we had to solve for in the end. We still have to find the perimeter of the kite. Now, why am I doing all this? Because the diagonals are going to matter. This is 6. The whole thing was 21. So this part is 15. Now I'm looking at another right triangle right here where the legs are 8 and 15. This one I'll also call x again. Is what I need to solve for. 8 squared plus 15 squared equals x squared. So x, to save you time, x is going to be 17. So I now found out what the length of this side here was, and I know that the one next to it, I know that the one next to it is also 17, and this one next to this is also 10. So the perimeter is 10 plus 10, which is 20, plus 17 plus 17, that's 34. 20 plus 34 is 54. A lot to do. You have to figure out where you're going. Just keep in mind you have those right angles there. So a lot of stuff you kind of have to know if you're going to do these problems, or at least have them as resources and be ready to go and work with them. Okay, the last slide before I finish off is really how I'm going to connect everything in terms of what things can be or what things must be based on properties. Going back to what we were talking about before, here's a quadrilateral. Everything that's a quadrilateral is also these things, meaning they're all four-sided shapes, they all have two diagonals, opposite angle sides, yada, yada, yada. Now it starts to stem off based on how many sets of parallel sides there are. And again, based on whoever you talk to, some might argue that a kite can have any set of parallel sides and it can form to be other things. For this example, it won't be true. And for every video I do, it will not be true. So for the quadrilateral here, either no parallel sides, one pair of parallel sides, or two pairs of parallel sides. From there, it starts to branch onward. If I just draw arrows, it starts to go down to something more specific from there. So for the kite, you can get more specific and maybe get a right-angled kite. I guess they could call that a right kite. Only one would be a right angle, though. Otherwise, one pair of parallel sides, either you have the trapezoid, which didn't really have any features other than consecutive angles being supplementary. An isosceles trapezoid also must then occupy that property. Consecutive angles are supplementary. They also had diagonals were congruent, stuff like that. Now the two pairs of parallel sides, it went to the parallelogram. Parallelogram had things such as opposite sides congruent, diagonals bisecting each other. Okay, so the rectangle, because it's a specific type of parallelogram, will also have those things that were true, and then it has more things, like the diagonals are congruent to each other, the angles are right angles, stuff like that. The rhombus also has what the parallelogram had, only we make the sides congruent. So the same properties apply with the and now they add in that the diagonals are perpendicular bisectors of each other, and that the angles are bisected by the diagonals, stuff like that. And the rectangle and rhombus, like I said before, they kind of merge together to make the square. And the square occupies all the properties of the rectangle and rhombus. So if you say that you have a rectangle, okay, say that you have a rectangle, that means you can potentially, your thing can potentially be a square. Now, if you have a rectangle, must your item be a square? No, but it can be. Okay, so in terms of the can be's, going downward are the can be's. If you have a quadrilateral, it can be this. If you have a trapezoid, it can be this. If you have a trapezoid, it cannot be a square, right? Because, etc. But these are the can be's going down the list of the arrows. Going upward are the must be's. If you have a square, you must have, for instance, a parallelogram. If you have a square, it means it means every property that is in a parallelogram is also in the square. The square has everything that a parallelogram has. So you can call a parallelogram a square. I'm sorry. A parallelogram can become a square, so you can call a square a parallelogram because it has parallel sides. That's all you need to know. So kind of like that. I just want to make sure that's well understood. Okay, and that's all. I know it was a lot, and that's all. Fin!